This part of the lecture, we are going to look at extension on Euler's formula. So Euler's formula prescribed that the critical load is equal to pi squared EI over L squared. We spent probably 1.5 lectures deriving it. Or the critical stress is equal to pi squared E bracket L over R squared. And the L over R, we know that this is known as the slenderness ratio. Okay. Now, to take note, the resistance to withstand buckling is not just based on Young's modulus, length, cross-sectional area. Now, the cross-sectional area will affect your second moment of area, but also how the structure are held, okay, on both ends. Okay, how the structure are held on both ends. So let's look at, there are 4 conditions that we're going to look at. So the condition number 1 is where you will have one fixed and one free end. One fixed end and one free end. Okay, so I have posted on Avenue to Learn these images. Can you all get them, please? Okay, so they're on Avenue to Learn. So the first one we're going to look at is at point A. This is what we known as free end, and the other side is fixed. Okay. So a thing to take note on this structure over here, we have to look at the boundary conditions, or we have to look at the conditions at the end. Okay. For the free end, if we were to call this our transformation, this is X, and this is Y, and this will be rotation about Z. The boundary condition for this case is, so we go about force in the X, force in the Y, and moment about Z. At free end, the reaction force is equal to 0. Reaction force in the Y direction is equal to 0. Moment is equal to 0. Whereas on the other side, where we have the fixed end, we have Fx, we have Fy, and we have moment about Z. What we know at the fixed end, none of this is equal to 0. Okay. So by viewing it as a figure, we know that on the free end, right, this thing can go left and right and up and down. Yes or no? Right? The up and down is not so significant. The left and right is more significant. Okay. So what? Okay. So when that's the case, the LE that I'm going to introduce to you is known as the equivalent length. Okay. The LE I was going to introduce to you is equivalent length. So the equivalent length over here, as you can see down here, is equal to 2L. Okay. It's equal to 2L, means the equivalent length is twice the original length. So if we were to apply Euler's formula, that states that the critical stress will be equal to pi squared E, and now the denominator is equal to LE over what? R squared. Okay. So when that's the case, this will be equal to pi squared E. LE now is equal to what? 2L over R squared. Okay. Now, so what? The thing now is so what, okay? So a while back ago, I think last week, we plot this this relationship. If I could find, bear with me, okay? Oh, okay. We plot this relationship, okay? So you have this. This is on Friday, okay? And I'm going to move this across. I'm going to use this. Yeah, I'm going to use this chart. Okay, so just to quickly recap what this chart does. Okay, so we have calculated a value of L over R of 88.86. 88.86 occur, if we go back, 88.86 occur when we have a structure looking like this. Okay, when our structure cannot move in the left or right. Okay, so I'll show the deformation pattern. So this is our deformation pattern. Okay. So for this case, remember we calculate where we have L is equal to, we calculate our L is equal to, I can't remember what our L is equal to. No, there's no L value. But what we have calculated, we calculated based on the stress critical is equal to what? Is equal to 250 times 10 to the power 6 Pascal. And our Young's modulus is equal to 200 times 10 to the power 9 Pascal. And I think our LE over here is equal to L. That's why we get 886. So just quickly show the formula that we are going to apply. So stress critical is equal to pi squared E over L over R squared. So we calculated that L over R is equal to square root. So Young's pi squared multiplied by 200 times 10 to the power 9. And now over here, this will be equal to 250 times 10 to the power 6. So the L over R, I want to be sure, okay? 200 power 9 divided by 250 power 6 times by shift by 1 times by shift by twice, square root the whole thing, 88.86. Okay, so that's how we get 88.86 down here. Now, what if now we have a structure based on condition number 1, where one end is fixed and the other free. Okay. So what happened now? LE is equal to what? 2L. Okay. So based on the modified or extended Euler, how many of you have can speak German? Okay. Where are you? Not you. You are yellow like me. Come on. It's okay. Now, you put up your hand, right? Anyone? Can anyone explain to me why this is the EU is Euler? Anyone? Any German descendant? Don't be embarrassed. Because it affects me a lot. My name is Eugene. So when it's Euler, it pronounced as Eugene, right? Okay, help me clarify something, okay? If your grandma is okay. Anyway, sidetrack a bit. Now back to here now, coming back. So based on Euler's, you speak German, yellow like me, speak German. The stress critical is equal to pi squared E divided by, now this is LE over R squared. Okay, right? So I'm going to move this across. Hold on. So from now on, don't call me Eugene, okay? It's Eugene, okay? Eugene, Euler, unbelievable. Maybe it's including the L, I don't know. Right, so now we calculate our critical load. So based on this, we calculate our critical, based on this, we calculate our critical load. So now this is 250 times by 10 to the power 6. And this is equal to pi squared, 200 times 10 to the power 9. So now the whole thing over here. So now we have 2L over R squared, right? So when we have 2L over R, this will be equal to pi squared, 200 times 10 to the power 9 over 250 times 10 to the power 6. So the L over R over here will be equal to 44.429. Okay. So that's the value. But what it actually means, more important, bear with me, okay? I need to get this diagram again. Pardon me. I think more important is what does it actually mean, okay? So what it means, 44.427 or 429, if I were to draw a red line somewhere around here, so I'm going to declare this is my 44.429, okay? Based on this graph or based on what you see, can someone tell me what is going on? Anyone? If one end is free, the other one is fixed, is the structure more prone to buckling or less prone to buckling? Higher tendency or lower tendency? Yes. Again? Higher. Okay, so it has a higher tendency for buckling to occur, right? Because you have to have a L over R. If it's lower, means you have to have a L over R. You have to consider buckling analysis at 44 point what? 429. Okay, whereas the other one is 88.86. Some of you are giving me the stare like, really? Okay, so let's look at this. Let's consider R as a constant. And we know, what's the formula for R? I can't remember. Let me refer. The formula for R is equal to square root I over A. Okay. So if we assume R is a constant, i.e. cross-sectional area,